realized that the other group was also doing the neuromuscular junction. So kind of, yeah, basic things right there.
A little more cucumber.
Signal sent to the synapse, synaptic vessel, ACH.
Stop
I guess something to point with. All right. ACH is released, bind to the receptors, and then onto the circuit. Okay, so we have a better drawing of what this is supposed to be. So when the neuromuscular junction is a nerve that hits the muscle, which causes the release of, I believe it's sodium, which then triggers the this guy right here, the T tubules, to release calcium, which then causes the muscle contraction. And so you have actin, then you have myosin, and on the myosin there is troponin and tropomyosin. And so when the calcium comes in and binds to the, calcium comes from the T tubule right here and binds to the muscle, or diffuses into the muscle, that causes troponin and tropomyosin to lift off of the myosin, and then the actin can then grab the myosin. So if this is the myosin, here's the actin, it's trying to grab it, it can't do it, and then when the troponin and tropomyosin leave, it can connect and then cause a contraction, which makes the whole thing move closer together. And that whole thing is it's Z line to Z line. So you have these kind of squiggly, let's see if you can see in here. Z line to Z line. So this part is going to get closer together. And so that's going to happen over and over again because the muscle's really long, it's multinucleated, it's got lots of mitochondria in it. And so when that happens over this long muscle cell, it shrinks. So you kind of have a breakdown of the different things. Again, better picture, more clear.
Let's talk about actin.
Yep. So we have troponin and we have tropomyosin. And so you can kind of see how they're a protein that is woven around the actin that inhibits the binding of the myosin and the actin. So when, as I said earlier, see how it's covering that little hole right there? That's where, the myosin wants to go. It wants to go into that hole, but it can't. So when the calcium comes in, it gets released, and then it can bind, and so that happens, and you get a contraction. And this can happen. It can be multi-stimulated, so you can have multiple stimulus that kind of compound the contraction to make it a longer, bigger contraction, but then you also have to deal with issues of tetanus and stuff because it doesn't have as long a refractory period as the cardiac muscle cell. So it can get stuck. It'd be like, ugh, you ever had your calf cramp? It really sucks. I had it happen in bed the other day. I was like, ugh. So, not fun. And okay. So these are all the different myosin molecules that are kind of woven together with the heads. The molecules. Okay, any questions?
Where did you say the calcium came from?
So the calcium is in the T tubules, to my understanding.
I thought.
No, go ahead.
No, go ahead. Don't say no.
I'm trying to throw down on you, I'm just saying.
I thought it was in the
Yeah,
endoplasmic
so,
Me too.
yeah, what do you think?
I thought, from what I was reading, I thought it was in the sarcoplasmic reticulum, and then there's the calcium channels on that, and then the sodium's released from the neuromuscular junction and all that. When the sodium comes in, it goes and releases another action potential down the T tubule, and then the T tubule is connected with like a protein complex, releasing the calcium out of the sarcoplasmic reticulum.
Okay.
And the T tubule is just like it conducts signals, and the calcium is kept in the SR, and then it also, the terminal cisternae can help store the calcium.
Say that.
Repeat that again.
You're right. The calcium is in the sarcoplasmic reticulum,
Mm-hmm.
which the terminal cisternae help store calcium, and then the T tubules just conducts signals. It's not really calcium.
Okay. Oh, gotcha. So it's coming from that signal. Okay.
Any other questions?
What is a T tubule? What is a T tubule?
I believe it's a protein.
Isn't it like you have the sarcolemma, and then it like starts to fold in and creates the, I don't even know what this is.
Isn't it like a space?
So what's inside the T tubule? What is inside the T tubule?
Calcium.
If it conducts signals, is it a nerve?
What is inside the T tubule? And you probably should have listened to Lindsay, or at least part of what she said. What is inside the T tubule? Why does the T tubule exist? What's the point of it?
Perpetuates another action potential.
To what?
Perpetuates another action potential.
What do you mean by that?
Sodium can flow down that conduction channel basically to cue the SR to release its calcium.
Why does it need to go down the T tubule?
Because there's a large surface area with skeletal muscle because it has a multitude of fibers.
So what's inside the T tubule?
Sodium. But I said it with confidence.
Be more general and specific at the same time. What is
Positively charged
inside the
ions.
T tubule? What is filling the T tubule?
Voltage gated sodium
Sodium ions.
channel.
Lindsay, say what the T tubule is again.
The T tubule is the part of the sarcolemma, and then it starts to, it's of the muscle cell, and it starts to keep,
So those are big words. I don't understand what sarcolemma is, so what's the sarcolemma?
Question. A plasma membrane of
Oh, let's stop right there. What'd you say?
plasma membrane.
Great. And so now what's it doing?
Releasing calcium.
Oh, well then stop. What is it? What's it doing? What's the sarcolemma doing?
Releasing calcium.
Releasing.
No?
I don't know
Say what you said before.
I forgot.
What's it do? What is the T tubule?
It's the sarcolemma.
Okay.
It's a fold sarcolemma. Is that right?
You guys have enough information. You just gotta listen to her, and she has to speak with confidence if she's saying it right. So, okay. I'll ask different questions. So, the sarcolemma is what?
Plasma membrane.
Great, we got that much. All right. What's on one side of this sarcolemma, and what's on the other side of this sarcolemma? You guys are being too specific for what I want. I want more general.
Sarcomeres?
Say that again.
Extracellular.
That's on one side, and
Intracellular.
intracellular's on the other. Oh, fantastic. Now what is the sarcolemma doing? Lindsay, what's it doing?
The barrier.
You said it like 3 times and it's been perfect, so don't lose confidence now.
Everyone's watching.
What's the sarcolemma doing?
I don't know now.
You said it. What's it
Oh,
doing?
it's folding in on each other.
Okay, great.
Okay,
It's
yeah.
folding. It's folding in on itself, yes?
Yes.
What is inside the T tubule?
Extracellular fluid.
Extra-
Say that again.
Extracellular
Say it
fluid.
one more time.
Extracellular.
Extracellular fluid.
Therefore, if you are inside the T tubule, what are you related to the cell?
Positive.
Outside.
Outside the cell.
Oh.
Got it? If you are inside the T tubule, you are outside the cell. The whole point of the T tubule is to continue what Lindsay said, which was to, you are the one that said there's more surface area, right?
No.
Who said that? Is that you? Okay, Emily said it. The whole point of the T tubule is that you've got a muscle that's thick, right? How do we activate the fibers in the very center of the cell when we're talking a big muscle, but everything that we're dealing with, like sodium ions, are microscopic? So the T tubule is made to make an invagination all the way through the cell or deep into the cell, so that as it travels down the T tubule, it can activate receptors and channels along that whole cell so that we can depolarize the whole muscle cell. Does that make sense? Rather than just the membrane, which we are used to only depolarizing. But now we're not talking about depolarization. Now we're talking about a situation where we have to have ions acting with proteins that are deep inside the cell. Everything you've learned so far related to depolarization is at the membrane. All the channels that we deal with are at the membrane. Yes?
Yes.
And what is our if we talk about a voltage change in the cell, if we're talking about a voltage change, for example, we tried to beat to death the trigger zone in the axon hillock the other day, right? Trying to figure out where things were.
Yep.
Right? We talked about the dendrites, and we talked about a sodium ion entering at the dendrite, yes? What happens to that sodium ion as soon as it enters? It's getting sent out, right? I want you to go one step further with this. We needed the threshold to be met at the trigger zone, yes? Where else at the trigger zone? At what part of the trigger zone? Don't say beginning, but where? Yeah, okay, the axon hillock is the same. You can interchange the words axon hillock and trigger zone if you want to. It means the same thing in a neuron. So at the axon hillock, where is the channel? Say again?
It's on the plasma membrane.
There it is. The voltage changes that we're talking about are voltage changes at the membrane. We are not affecting voltage deep inside the cell at all. We are changing the voltage at the membrane where those channels are, and that's it. So if we were to try to take calcium, for example, and flood calcium into the membrane, and what they're telling you right here is that calcium is necessary, yes, to cause a contraction. But if we flood the cell membrane with calcium, what's going to happen to that calcium right after we flood the cell membrane? It's going to get sent right back out again. In this case with calcium-sodium exchanger pumps. It's going to get sent right out again, yes? How does that help us with the middle part of the cell where these proteins are found? It doesn't. So skeletal muscle, all muscle, creates T tubules by folding that sarcolemma on itself so that extracellular fluid can go all the way down deep inside that cell, which for all intents and purposes gives us more cell membrane going into the cell. So instead of the cell membrane being right here at the surface, the cell membrane now goes inside the cell, right? So this T tubule that we have here now can affect deep inside the cell. So we don't just get a depolarize up here at the cell membrane, we get a depolarization clear down here where it can actually start affecting those intracellular things that are going on in there. Does that make sense? Question? Okay, so now, depolarization of the T-tubule causes what?
The release of calcium.
Causes the action to
How?
Which then causes the,
How? Releases calcium from where and how? And this is critical, because this is hugely different than cardiac muscle right here. This is a critical moment. We're at a very important moment for anybody who wants to pay attention. How does depolarization of the T-tubule cause the release of calcium? Where is it coming from, and how is that happening in skeletal muscle?
It's coming from the terminal cistern.
I don't know what that is. That's a big word. Help me out.
It's,
I gotta remember, I've got like a kindergarten brain.
so the T-tubules,
Yep.
they have, little areas next to them that hold on to calcium.
What are those areas called?
Terminal cisternae.
What else? What is the terminal cisternae?
Also membrane.
A large area of smooth endoplasmic.
That what? Because you can just
Sorry.
read what they got there.
Hold calcium release.
Who said that? What's the triad?
The triad is the T-tubule terminal cisternae sandwiched.
What is the meat of the sandwich, and what's the bread of the sandwich?
The terminal cisternae is the meat, and the T-tubule, the T-tubule is the bread.
Great. Not quite. Try again.
So the reverse of what I just said?
Perfect. So now say it again so everybody can understand.
I've forgotten what I said, but.
What's that?
Sarcoplasmic reticulum is the bread, and the T-tubule is the meat.
Fantastic. So one depolarization of a T-tubule depolarizes two different directions within that skeletal muscle fiber. Does that make sense? Okay. And that's going both directions into two different SRs. Why is that important? Who cares?
Muscle contraction.
You know, it's the whole muscle instead of not like part of it. Individual
Okay,
fibers.
yes, I asked a poor question. Why do we care that the SRs are anywhere near the T-tubule?
Because that's where the calcium.
Because what?
That's where the calcium's held.
Because that's where the calcium is. Great. How does it come out?
Voltage gated channel.
Calcium channel? Didn't answer your question.
I need a lot more information.
Voltage gated channels combination change the.
Voltage, say it again. What kind of a voltage gated channel?
Sodium.
Voltage gated calcium channel?
I don't know. Help me out. Figure it out. Remember any of those things. Pull it from your brain. I know it's been in there at some point in time.
What's the question again?
How is calcium released from the SR in skeletal muscle? How is calcium released from the SR in skeletal muscle? And this is a critical difference between skeletal muscle and cardiac muscle. How is calcium released from the SR in skeletal muscle?
In the presence of sodium, there's a voltage gated channel that will exchange that outer cellular space that has sodium in it with calcium. And you mentioned it like 3 seconds ago.
Are you talking about like
Not in this case.
the time, like fast calcium? Is it compared to the slow?
Nope. Here's what I want to know. inside the cell, there is a load of calcium. That calcium is sequestered where? In this thing called the sarcoplasmic reticulum. Yes?
Yes.
In this place called the SR. This calcium, by the way, does not in any way, shape, or form interact with the rest of the body. So when we talk about hypo or hypercalcemia, this calcium has nothing to do with it. Okay? That's all blood-related calcium and extracellular calcium. That's not this. You've got a load of calcium sequestered in the SR. In order to have a contraction, calcium has to be released into the intracellular space to interact with troponin. Yes?
Yes.
That calcium has to come out of the SR. How? What's going to cause it to come out? And somebody has got to come up with 3 letters that go together
ATP?
that are not ATP.
Acetylcholine.
That's just an abbreviation of neurotransmitter.
We're just throwing
No?
3.
3 letters.
How many 3-letter things do we know?
Okay, there is a receptor that you have to know. There is a receptor name. There is a very specific receptor in the T-tubule. Close. You're almost there.
What did you say, Sarah?
L-type calcium channels, calcium activates ryanodine receptors on the SR. This receptor senses.
What are you reading right now?
What?
What are you reading right now?
Pathophys.
Ah, say that. Stop everything. Everybody shut up. Stop everything.
So I Google it.
Say it.
DHP receptor.
Remember the DHP receptor?
No.
Oh my goodness.
D or T?
DHP. Delta HP.
Is that really a name for this? I'll take it again.
What does it stand for?
The DHP receptor. What's it stand for?
Doesn't tell me that on the Google side.
I'm sure you can Google it.
Dihydrogenate receptor.
There we go. Can we try to get that better in solid English?
Right, right, 2 hydrogens.
I can spell it for you. Dihydropriodine?
Oh my goodness. Okay, so you have some work to do. This DHP receptor is mechanically linked to the SR. This DHP receptor is mechanically linked to the SR. It is voltage activated. So when the T-tubule is depolarized, much like in the, don't equate this completely, but much like in the axon, remember how we had an all or nothing action potential? And the very last channel was a calcium channel? You remember that? So the very last channel was different, and it caused something different. It's similar here in that as it travels down the T-tubule and we depolarize the T-tubule, we get to these DHP receptors. When the DHP receptor is activated, it's voltage activated. When it's activated off the depolarization of the T-tubule, it is mechanically, physically linked to the SR. And when it is activated, there is what we call a conformational change. You'll hear that quite often in here as we go through. Conformational change means it changed its shape. When it changed its shape, it pulled a channel open that allowed calcium to come out of the SR. Make sense? So far? As the calcium came out of the SR, it was now flooding that intracellular space. And it wasn't near the membrane. That calcium is not near the membrane. And because that calcium is not near the membrane, it's not being sent out as quickly, which is good for us because we want a contraction to happen. So that calcium is flooding that intracellular space right where our cross bridges are, our actin and myosin. It's attracted to the calcium troponin, the troponin C, the troponin that's activated by calcium. It's activated by that. When calcium plugs into that troponin, it causes another conformational change in the troponin, a shape change. When you see that shape change in the troponin, that shape previously was covering a site that myosin is attracted to, and we had that shape change in the troponin. That site is now available, and now myosin is attracted to that G-actin protein. Does that make sense? I'm going to ask the dangerous question.
No, it does not make sense.
What doesn't make sense about it?
About the last 15 minutes.
Be more specific.
About the last 15 minutes.
YouTube.
So when calcium goes through a DHB channel, does it automatically go through the intracellular fluid straight into the SR, or does it have to be carried through the ryanodine channel to get into the SR? Does that make sense? What I'm asking?
I'm not sure if we're cart or horse.
Huh?
I'm not sure if we're the cart or the horse. What do you
Yeah,
want to see?
I guess that's my confusion. If you've got calcium in the T-tubule,
Calcium's not in the T-tubule.
I'm sorry.
Calcium's in the SR.
It's intracellular.
See if this answers your question. I don't know if it does or not, but let's find out. Interspersed throughout all of this area. The SR surrounds everything. I can't draw three-dimensional. I suck. I'm sorry. So here we have actin and myosin down here. We have the SR going on right here. Okay? Here's my T-tubule. Here is my neuron. Okay? My neuron is going to release ACH. ACH is going to activate nicotinic receptors. Nicotinic receptors are on sodium channels that are then going to allow sodium to come into that cell. That sodium that comes in is going to start the depolarization of that membrane. That depolarization is going to activate more voltage-related channels. And there are voltage-related channels all across the membrane and down the T-tubule. This voltage is going to activate this one, it's going to activate this one, it's going to activate this one, it's going to activate this one, and we've got sodium coming in all along here. And getting pumped out because we've got sodium, potassium, ATPase pumps there as well. Yes?
Yes.
It is eventually going to here's another SR down here, right? And we talked about the triad, which was what we call the terminal cisternae, which is a T-tubule and two SRs together. This makes up the triad. It's the T-tubule and the things that it affects on both sides. The very last channel down here, or the very last voltage-regulated receptor, is a DHP receptor. When that DHP receptor is activated, it is physically attached to a calcium channel. When that DHP receptor is activated, it is going to physically change the shape of itself and open a channel where calcium can come out.
So where
calcium is not inside that cell, it's at the same level that the T tubule is, it's like on the outside.
No, this is all intracellular right here.
So-
This is extracellular.
Right.
That is inside the cell.
So the calcium then goes further into the cell? or-
Correct. The calcium is sequestered inside a closet inside the cell. The
Okay.
SR is a trunk, is a closet, a garage inside the cell. And we are opening that garage.
Okay.
And so the sodium depolarization is taking place
On the
the
membrane
membrane of the
of the muscle cell. That's correct. We open that calcium channel, and calcium is able to flood out into this intracellular space, where it now has access to the actin.
Is there only one calcium, voltage-gated calcium, or is it all over the?
That's all over the SR.
Okay.
These DHs, we simplify A and P by saying there's one of everything.
Okay.
We're talking there's hundreds of these things that are all opening at once. This area is getting flooded with
Okay, that
calcium.
makes sense.
Okay? Then we have on the SR, we have calcium, ATP ACE pumps that are bringing calcium back into the SR. It's resequestering calcium. And on the membrane, in several different places on the membrane, we have calcium, sodium, exchanger pumps. They pump some 5,000 or so calcium molecules per second that are pumping calcium out and sodium in. And then that's regulated by a sodium potassium HPS pump that is then taking sodium back out and putting potassium back in its place to get all the electrolytes re-situated where they're supposed to be at rest.
Okay, let me go over the last part one more time. So the calcium goes back from the sarcolemma back into the SR,
And to the extracellular space
into the
through
extracellular
the
space,
exchanger pump.
activating the calcium-sodium pump.
Say that again.
Back into the extracellular space. That goes,
Calcium in the intracellular space, because this is happening all throughout. I've got calcium flooding up here, calcium flooding up here. So some of that calcium is resequestered into the SR,
yeah.
and some of that calcium is sent out
Oh, it's in.
with that exchanger pump.
Okay.
And the way that that pump works is that when there's the presence of sodium and calcium together, it'll spin calcium out and spin sodium in.
Okay.
And then the sodium potassium ATPase pump will correct the sodium issue,
So it's
taking
sodium,
sodium back out and putting potassium back in.
Okay.
so sodium, potassium, ATPase pump is the last one you mentioned, right?
That is,
Okay.
which we have a cajillion of.
And you said that this process isn't affected by hypocalcemia in the rest of the body.
What I said is that this calcium that is in the SR has nothing to do with any other function in the body where calcium is present. So anytime we say the terms hypo or hypercalcemia, anytime we talk about calcium loss, anytime we talk about anything related to calcium, we are never talking about that calcium.
But I thought having hypocalcemia, like one of the signs was like muscle stuff.
Because of depolarization issues, not because of calcium that's in the SR. And certainly by the time, if at some point in time when you start lowering your blood levels of calcium, if they're low enough for long enough, then we'll start losing the calcium out of the SR as well over the course of time. But for example, this, when we talk about the charge of a cell, right, the overall charge of a cell is what, positive or negative? I have a cell right here. what's the resting membrane potential of a cell? Give me a resting membrane
Negative
potential.
Negative 70.
Negative 70. So you've chosen the resting membrane potential of a small neuron, right? If it's negative 70 here, what do you think it is here? Higher or lower than negative 70?
Lower,
Is it more positive or more negative?
more negative.
Yes, more negative. It has to be very, very negative here because what happens to charge as it travels away from its center? Becomes less. It gets more and more neutral. If we made this cell large enough, if we had a cell the size of Noah, the resting membrane potential would not be negative 70 if it started the same charge as what all of our cells are currently charged at. The center part of the cell is very, very negative, and it gets less negative as you move away from all the proteins and all the things that are in the center of this cell. As you move towards the outer side of the cell, it's the least charged that it can be, and it's charged at negative 70.
So when you say very negative, like what is very negative?
Well, it depends on the size of the cell and the type of the cell. But quite a bit more negative. I mean, we're anywhere
Like twice as more negative?
anywhere from 20 to double, right? But look at these positive ions you have in here. These calcium ions, we've got an abundance of calcium ions in here, right? The SR prevents this calcium from having any charge activity to the cell. The SR completely buffers that calcium from having anything to do with the charge of the cell. If it didn't, and we had all that calcium in there, the cell would already be depolarized all the time, because that's a lot of positive ions that would gravitate towards that membrane. So the SR sequesters that calcium and prevents that calcium from having any interaction with the cell at all until it's opened and allows the calcium to come out.
There's no way we're gonna do this right.
You're right away. But here's the deal. How is that different in cardiac muscle?
Cardiac muscle, there are calcium leak channels that lead you to constantly drifting towards depolarization.
Okay, so that's an autorhythmic cell, and it's not calcium based, it's sodium, but we'll come back to those. One of the other groups has
There's
that.
like late.
And we did,
There's like
we did our
delayed
best to cover that.
potassium.
There is something very, very different about this spot right here in cardiac cells compared to muscle, skeletal muscle. Anyone remember what it is? Yes.
It's the calcium, it's the calcium-induced calcium channel, right?
Yes.
So
Yes.
it stays open.
Yes. The depolarization of skeletal muscle is completely based on sodium. Sodium enters, sodium causes the depolarization of other sodium channels until it gets to that DHP receptor, which isn't ionic at all. It's not a channel, it's a mechanical receptor. As long as everything is depolarized via sodium down that T-tubule, it'll eventually get to that DHP receptor and pop that calcium channel open. That's not the case in cardiac muscle. In cardiac muscle, there is no mechanical link between the SR's calcium channel, and what's being depolarized on the membrane. In the case of calcium channels, this last, it's still a DHP receptor, but it's not mechanically linked. This last channel down here, or this last receptor down here, is going to, instead of being mechanically linked, it's going to open a channel. What kind of a channel? Calcium. And that's going to allow extracellular calcium to come in. That extracellular calcium, although it does have an effect on our actin, is not we're not interested in it having an effect on the actin, although it does, that calcium will engage a calcium channel right here that is activated by calcium. We call it a calcium-induced calcium release. That calcium that comes in will activate this channel, which will then open to allow more calcium out.
Why doesn't the calcium in the SR activate its own?
Because the receptor's on the outside of the SR. So extracellular calcium will then activate the SR channel to let SR calcium in that will then allow for a contraction to happen.
How does it ever close if it's constantly being stimulated by calcium?
Well, it closes because when the channel is opened, it's got an absolute refractory period. And during the absolute refractory period, it's closing. Then it's depolarized again.
But it is longer, though.
It is.
A lot
Which we
longer.
should find out pretty soon.
Yes. I'm ready, Mons.
Are we making some connections all of a sudden?
I was like, to the next one we go.
Okay, come on.
Right?
Do we find
So-
circuit pumps on this?
Say again?
Do we find circuit pumps on this?
Yes, your calcium HPA pumps are still here, as are your calcium sodium exchangers in cardiac muscle. That's still happening
Boom.
to resequester everything, okay? Which means if somebody is hypocalcemic, what does that word mean?
Low calcium.
What does that word mean? So someone finished it.
Low calcium levels in the blood.
There you go. Pertaining to deficiency of calcium in the blood.
So if someone's hypocalcemic, they'd actually have issues with cardiac muscle, but not skeletal muscle.
Yes.
Is it cardiac, is that channel's produced by calcium?
Yes. So, if your body was void of all calcium, you would never be able to have a muscle contraction of the heart. But you could have a muscle contraction of the skeletal muscle if you were devoid of it in your blood.
So is that also the opposite if you are hyper, and that's why people have calcium channel blockers? Or they,
That is not why people take calcium channel blockers. You can be hypercalcemic, and it does cause some issues, but not quite as many with heart contraction. We good so far?
Well,
It's a huge difference. It's a huge difference.
If you're a hypercalcemic, the reason which causes issues is because of the refractory period on that channel.
If you were
So
hyper, yeah,
You
it doesn't
could have
matter.
all the bands of calcium, but this is only gonna
Yes.
open for a determined amount of time.
Correct.
It's like, I don't care how much calcium it has.
Yes, correct. Amongst other things, yes. Good?
we're ready.
I will also tell you that nearly 100% of the skeletal muscle contraction comes because of SR-related calcium. That's not the case in cardiac muscle. In cardiac muscle, and I don't know the percentage off the top of my head, but maybe 60% of cardiac muscle contraction comes from SR-related calcium. The rest comes from other calcium channels that we have actually on the membrane that bring in calcium also. So extracellular calcium affects cardiac muscle both by allowing SR calcium to come out and by flooding the intracellular space with calcium. So calcium plays a different role. Calcium plays the same role in contraction at the actin myosin level. How that calcium gets there is different in cardiac muscle than with skeletal muscle. Good?
That was great.
I didn't even notice no move.
Good? We will get into talking about things like cortisone. And what is cortisone?
Calcium channel blocker.
Which calcium channels are we talking about? Why does it have an effect? Why are we using it related to high blood pressure? Why are people taking it related to high blood pressure? Why do we give it for AFib and aflutter? Related to these topics, where these calcium channels are and what they affect in terms of their depolarization process. And why they don't affect skeletal muscle in the same way, yes, right? And we haven't even talked about smooth muscle yet. Okay.
I'm assuming this means the next.
One quick break?
If I had to guess.